In this video, we are going to talk about inverse trigonometric ratios. So this really is not anything brand new. It's the same concept as regular trigonometric ratios, but instead of finding missing sides, you use inverse trig ratios to find missing angles. So the three inverse trigonometric ratios are sine inverse, and that's noted as sine -1. Cosine inverse, which is cos or cos -1, and tangent inverse, which is tan -1. So we're just going to walk through a few examples of how to identify the inverse trig ratios of an angle. So if I'm going to start with using the top angle in this triangle, again, we will call it theta, just like we did in the last video. If I want to find the angle theta, all I would have to do is set up the trig ratio. So my first option is to use sine inverse. So remember, we know that sine is opposite over hypotenuse. Okay, so previously what we did was we labeled the sine of theta is equal to the opposite, which was 3, over the hypotenuse, which is 5. Well, I can rearrange this equation so that it says theta is equal to, or the angle measure is equal to, some value. So if I want to write that theta is equal to something, so if I were looking for this angle measure, I would simply have to perform inverse operations to get rid of the sine part of this equation. Because if I want to isolate the theta, if I want to get theta equals something, then I have to get rid of the thing that's on the same side as the theta. So sine isn't really like the other regular operations that we come across. It's not like multiplication, division, addition, and subtraction. It's actually a function. So we can't just like do the opposite of sine without knowing what that opposite version is. That's where inverse trig ratios come into play. So if I want to get rid of this sine, I would use its inverse, or I would take the inverse of it on both sides. So I'm going to take the inverse of sine, which is sine -1, and move it over to the other side. Now I also have 3 over 5 still on the right side, and that stays in parentheses. So essentially it's the same information, it's just written in a different way. We just rearranged that equation that we started with in the last video. So you can use the same process of saying sine theta equals 3 over 5, just like we did previously. But if you're trying to solve for theta, or if you're trying to find a missing angle, you would have to use the inverse of that trig ratio. All right, let's do another example. So again, let's say I am still using the top angle here, theta. Well, let's talk about cosine inverse. So we know that cosine is the adjacent over the hypotenuse. So from the angle that's marked, the adjacent side is 4. So the cosine of the angle that's marked is equal to the adjacent over the hypotenuse. Well, what if I wanted to know what is the measure of that angle? All I would have to do is take the inverse of cosine on both sides. So theta is equal to cosine inverse of 4 over 5. Now if we wanted to use the tangent of the marked angle in order to find that measure of the angle, then we would use tangent is equal to opposite over adjacent. So the opposite is 3, the adjacent is 4. So the tangent of that angle is equal to 3 over 4. Using these two sides, if I wanted to know what is the measure of that angle, I would just rearrange that equation. So take tangent inverse on both sides. So we have tangent inverse of 3 over 4. So I wanted to just mention that, notice how once I move the tangent to the other side and take its inverse, I don't have a tangent on the left anymore. That's what got rid of it. That was the whole point of using the inverse. It's kind of like, let's say, if I have an equation, 3x equals 12, right? If I want to solve for x, if I wanted to get x by itself, then I would have to use inverse operation. So if I have 3 times x, I have to do the opposite of multiplication. I'd have to do division on both sides. So when you do inverse operations, that item always goes away. So we get x equals, right? So using inverse operations with trig ratios is the same idea as using inverses with any equation in general. Once you use the inverse, it goes away on one side. Okay, let's actually put this into practice. So if you are using inverse trig ratios, it's not always the case that you're given all 3 sides. Sometimes you're only given 2 sides, but that's all you need. As long as you have 2 sides of your triangle, you can find any of the angles within that triangle. So let's say we want to find the measure of angle x in the triangle that's given here. Okay, well, just like we did before, we want to identify what information do we have. Okay, so if this is my angle, I want to know what is the 4 and the 5 from this angle. So directly across, we have the 4. So that makes this the opposite side from the angle x. Then we have directly across from the 90 degrees, we have this one is labeled 5. So that one makes this the hypotenuse. So if we have opposite and hypotenuse, we know that that is sine. So the sine of angle x is equal to the opposite, which is 4, over the hypotenuse, which is 5. Well, if I want to know what is angle x, if I want to solve for x or get x by itself, then I need to get rid of the sine. And I can't get rid of the sine unless I use its inverse. So I'm going to have x equals sine inverse of 4 over 5. Well, that doesn't help me very much because I don't know what that value is. So we can plug it into our calculator, right? So I don't need to type in x equals. All I want to know is sine inverse of 4 over 5. So I'm going to go to functions, and you see where it says sine -1 or sine inverse, and then type in 4 divided by 5 within the parentheses. So here we have our decimal number. Remember how last time I showed you how you can toggle between radians and degrees? Notice this says x degrees. We have not learned about radians yet, so if it's in radians, you're going to get some funky looking number. 0.9 degrees wouldn't make a whole lot of sense since this angle in the triangle appears to be more than 1 degree. Just double check that, make sure you're in degree mode. So we got 53.13 if we are rounding to 2 decimal places. So x is 53.13 degrees. All right, let's do another example. In this one, I'm going to show you where you might not have the opposite side. What if you have the adjacent side to the angle that you're trying to find? So 3 would be the adjacent side, and 5 would be the hypotenuse. So if I have adjacent and hypotenuse, that goes with cosine. So the cosine of angle X is equal to, the adjacent side is 3, hypotenuse is 5. Well, if I want to find the measure of angle X, I have to get rid of the cosine on this side of the equation. So I have to use its inverse. So X equals cosine inverse of 3 over 5. Okay, so under functions, we can go cosine inverse, 3 divided by 5, and we get 53.13. Okay, I just use these numbers 3, 4, and 5. That is a special type of triangle that you'll learn about later on, but it's just 3 easy numbers to work with, so that's the reason I'm using them over and over. But it doesn't matter what those numbers would be. This is the process of finding angles using inverse trig ratios. Okay, and then finally we could do a third one where if you didn't have the hypotenuse, if you just had the opposite and adjacent, the same process would hold. Right, so this time let's look at this triangle and see if we were only given the opposite side and the adjacent side, then which trig ratio would we need? So if I have opposite and adjacent, that goes with tangent. So the tangent of X is equal to opposite over adjacent. Okay, same thing. If I want to get X by itself, I want to know what that angle is, I would use inverse tan on both sides. So X equals tan inverse of 4 over 3. And again, type that right into Desmos, or if you have a graphing calculator, these symbols are on your graphing calculator as well. So tan inverse 4 divided by 3. And again, we get X is 53.13. Okay, so I just showed you how to use each inverse ratio within the same triangle. So no matter which two sides you're given, you can always find the missing angles as long as you are using your correct pairs of sides.